This is a demonstration of a mathematical machine I made a while back based on Fourier series. Fourier series is a way to approximate any mathematical function, either real or complex, just as a weighted sum of sines and cosines. All you need to do is to compute those weights according to which you are going to add the sines and cosines to approximate your input function. Another cool way and less confusing way to think about the problem is to think of the combination of cos and sine waves in the complex plane. So you see, cos theta plus I sine theta, according to famous Euler's formula, is just e to the power I theta, which basically tells us that the combination of cos and sine waves in the complex plane is just a vector rotating in a complex plane around the circumference of a unit circle, which means that our whole problem is transformed to rotors, rotating vectors, and all we need to do is to compute the initial state of each rotor, which comprises of three things represented by this class, the rotor state. It has three things: frequency of that rotating vector or rotor that is arbitrarily decided, and the coefficient, which comprises of two things: the magnitude scale, which defines how long or short that rotating vector must be, and the initial phase, the starting angle of that rotating vector. And once you compute all these states of all those rotors, then you combine each of these rotating vectors tip to tail, then you set them off spinning, and the final tip will trace out a graph approximating your input function. That, I believe, is a lot of math. So let me demonstrate this with a simple example of a step function. The step function is basically a function that turns on and turns off. It looks like this. So this line here, this is for turning off 0, and then turns on 1, and then off, then on. So we have to approximate this function just as a weighted sum of sines and cosines. So this is the program, and I'm going to select this step function from here. There it is, the step function. You can see in the background it is loading all those rotor states. So a rotor state comprises of three things, as I said earlier: the frequency arbitrarily chosen, the coefficient representing the magnitude of that rotating vector, and the initial phase. All of that information is stored in a complex number. This is the real part, this is the imaginary part of that complex number. So let's start with only one rotor. So you can see one rotor does nothing. As I add another rotor, which means adding a sine and a cosine wave. So in the wave representation, you can see it's a normal pure sinusoid wave. It's not a step function yet. If I add another rotor, nothing happens. If I add another rotor, you can see there's not much change. But as I keep on adding rotors, you can see the approximation by adding these rotors, it approaches to the original step function. So let's say I increase the rotors to 15. So you can see it's looking like a step function now a bit. As I keep on adding the rotors, the approximation will converge finally to the step function. So at the rotor 27, you can see at rotors 35, see it is approaching to the step function. As I increase the rotors to 50, the change is much abrupt now. Then as I increase to around 200, then it is almost a step function now. Let's say I increase all the way up to 1000, and it's now completely a step function, almost completely a step function. You can increase the speed of the simulation to contract the domain range of the step function. You can decrease the simulation speed to expand the domain of the input function. So basically you can stretch in, stretch out, you can translate, you can zoom in or zoom out, basically scaling and translation. You can invert the axes. You can see the graph of the input function as approximation. For a step function, the graph consists only of 2 points. The upper point here represents the on state, and the down point here represents the off state. Here is another function representing a musical note. Can increase the simulation speed so that it will go faster. You can disable the auto track to see the graph, invert the x-axis or the y-axis, flip it along any axis. You can disable the joining of the points. You'll see individual points then traced by the approximated function. Enable the joining of the points to visualize the interpolated graph. You can disable the color cycle, enable the color cycle. You can pause, play, you can translate, you can zoom in, scale up, scale down. You can see the wave representation of this graph. You can draw it sideways so it gets clear of the rotors, or you can enable the auto track and go full screen to view the animation. Now, to define a function as an input to this mathematical machine for approximation, all I need to do is to implement this complex domain function interface, which is just an extension of complex function and domain provider. So as an example, the step function implements this complex domain function interface. This is where I define the domain start and the end point, and this is the actual logic of the function, which maps a double precision input to a complex number in the complex plane, and then the machine draws out the graph in the complex plane of this function as approximation using the weighted sums of sines and cosines. Another example is like this character R, which represents a R character, R alphabet. This is the actual logic of that character. This is the character C, and when I combine these two, it creates a function which represents my name RC. And if you don't know programming or how to implement these functions, you can define external functions. So to do that, let's say I have this function here, this emoji, and I want to define it in some way and then as to give it as input to this machine for approximation. So all you need to do is to create a SVG, scalable vector graphics file, which I have here, and you have to copy this data, this vector data, inside the SVG DOM element. You can copy it, and then you have to go to this external functions directory. This is in the project source. This exe stands for external functions. You can define any number of external functions using the SVG vector data. Let's say I create a text file named test.txt and I paste the vector data inside this file, and then I launch the program. The program automatically loads all the files, all the functions, external functions. You have to select that function. So that function is this text external. This exe stands for external function. So when you select it, it starts loading the rotors based on this functions.